So imagine you're at a local coffee shop, right? You order a coffee for $3 and you hand the barista a crisp $20 bill.
A pretty standard morning routine.
Exactly. And the barista hands you $17 and change. You take it, you know it's right. The barista knows it's right. The cash register literally did the math.
Right.
But what if someone suddenly stopped you right there, held your feet to the fire and said, "Hey, prove to me that 20 minus 3 is 17."
Oh, wow. Like, mathematically prove it.
Yeah. Like, use the fundamental laws of the universe to prove that this basic transaction is correct. Most of us, I mean, you'd probably just freeze.
Oh, absolutely. I think everyone would. It's the moment the ground kind of falls out from under you.
Because the math we use to run our entire civilization, the math that keeps airplanes from falling out of the sky or builds our skyscrapers, it's something we just take entirely on faith.
We do. We trust it implicitly. We spend our whole lives operating on top of this massive invisible scaffolding of logic.
Right.
I mean, you don't pause at the register to consider the complex biomechanics of your leg muscles holding you up. And you definitely don't question the fundamental properties of the number 20.
No, you just take your coffee and leave.
Exactly. But if that logical scaffolding were to shift even a fraction of an inch, well, everything we know about reality would just collapse.
And that is exactly what we're dismantling and, putting back together in this deep dive. We are taking the numbers you use every single day and breaking them down to their absolute most atomic rules.
Stripping it right down to the studs.
Yes. We've got a really foundational text guiding us today. It's Michael Spivak's notoriously rigorous book, Calculus. Specifically, Chapter 1.
Right, which has this deceptively simple title, like Basic Properties of Numbers.
Yeah, deceptively simple is the perfect way to put it. Because our mission today is to reconstruct the entire universe of numbers from scratch.
Which is quite the undertaking.
It really is. I mean, we all know how to add and subtract. We memorize the times tables in grade school. But very few of us actually know the why behind those operations.
Yeah, the mechanics under the hood.
Right, like why exactly is a negative times a negative positive, or why is dividing by 0 the ultimate mathematical sin? So we're going to build up to those profound logical proofs, but, keep it in plain, accessible language.
And what's fascinating here is that this isn't just a math review. We are engaging in a real masterclass in analytical thinking.
How so?
Well, by starting from absolute scratch, we strip away everything we just assumed to be true. And by doing that, we get to build a flawless logical framework.
Like learning how to construct an argument where every single microscopic step is justified.
Exactly. It guarantees the correctness of our daily calculations. It really trains you how to think critically, to identify the hidden assumptions in your own reasoning.
Okay, so let's build this engine of reality piece by piece. According to Spivak, to construct the entire universe of everyday mathematics, we literally only need 12 properties.
Just 12 rules to govern everything.
It's wild. And I guess the logical place to start is the architecture of addition. So that's properties 1 through 4.
Yeah, let's look at addition at its most basic fundamental level. The very first thing Spivak points out, and this is a structural limitation that really trips people up when they think about it, is that addition is strictly an operation performed on pairs of numbers.
Wait, pairs? Like only 2 at a time?
You could only ever add 2 things at a time.
Okay, I'm going to challenge that immediately because if I look at a grocery receipt and my coffee was $3, my pastry was $4, and my tip was $2, I just add 3, 4, and 2 in my head all at once to get 9.
It definitely feels like you're processing them simultaneously.
Yeah, I'm looking at 3 numbers, I'm adding 3 numbers.
You think you are, but you aren't. Your brain is actually executing this biological and cognitive shortcut. Yeah. Underneath the hood, your mind either added the 3 and the 4 first to get 7, and then added the 2 to get 9. Or, maybe you naturally group smaller numbers, so you added the 4 and the 2 to get 6, and then the 3.
Oh, okay, I see what you mean.
Right. You physically cannot process 3 independent mathematical values simultaneously in a single unified operation.
They have to group them into pairs. Wow, okay.
And that unavoidable reality is what brings us to property 1, which mathematicians call associativity.
Associativity. So if we only process pairs, this is the rule that dictates how we group those pairs.
Correct. It formally states that if you have 3 numbers, let's just call them A, B, and C, it does not matter how you group the pairs to do your addition.
Oh, okay.
The group of A plus B, calculated first and then adding C, is flawlessly equal to A plus the group of B plus C.
Now, on the surface, that sounds painfully obvious. Like, of course, 1 plus 2 plus 3 is 6, no matter how you slice it.
Right.
If I have an apple, 2 bananas, and 3 oranges, I have 6 pieces of fruit. Why does Spivak make this the very first, most crucial law of the mathematical universe?
Because without property 1, a string of numbers is mathematically meaningless. Imagine a universe where grouping actually did change the answer.
That would be a nightmare.
Total chaos. If adding A to B first gave you a different result than adding B to C first, we'd be completely paralyzed. Spivak notes that if you have just 5 numbers to add together, there are exactly 14 different ways to group them using parentheses.
Wait, 14 different paths just to add 5 numbers?
Yes. You could add the first 2, take that result and add it to the third and the fourth, or you could add the last 2 together, then add the middle one to that. 14 distinct computational paths.
And property 1 is the ironclad guarantee that all 14 of those paths lead to the exact same destination.
Exactly. That is why we can confidently ignore parentheses and long sums and just write A plus B plus C. Property 1 gives us freedom from that chaos.
Okay, let's unpack this. It's the rule that allows us to be efficient without breaking reality. Like when a massive spreadsheet calculates a column of 10,000 numbers, it doesn't matter which pair it adds first. The total is stable.
Stability is exactly what we are building here.
Yeah.
Now, property 4 works hand in hand with this. It's called commutativity.
Commutativity.
And it simply dictates that A plus B is exactly the same as B plus A. 2 plus 3 is 3 plus 2. The order of the physical symbols on the page just does not matter.
So associativity is about the freedom of grouping, and commutativity is about the freedom of order.
Precisely. Together, they let us juggle quantities however we want in whatever sequence is most convenient.
Okay, but shuffling positive quantities around doesn't give us a complete system, right? Like, we are missing the anchor. We're missing 0.
And that introduces property 2, the additive identity, 0. Property 2 says that there exists a number, 0, such that any number A plus 0 equals A.
5 plus 0 is 5. A million plus 0 is a million.
You got it.
But again, this feels like stating that water is wet. Why does the universe need a formal law declaring that adding nothing changes nothing?
Because introducing 0 allows us to introduce the concept of undoing an action. It paves the way for property 3, which is the concept of additive inverses.
Additive inverses, okay.
Yeah. For every single number A in existence, there exists a corresponding number, negative A, such that A plus negative A equals 0.
Makes sense.
And here's where we have to completely shatter a childhood illusion. Are you ready?
Lay out me.
Subtraction, as a fundamental concept, does not actually exist.
Okay, that is a massive claim. Subtraction is literally half of what we learn in elementary school. What do you mean it doesn't exist?
Well, in this pure logical framework, we do not define subtraction as its own unique, independent operation. We define it simply as the act of adding an inverse.
Adding an inverse.
Right. When you write A minus B on a piece of paper, what you are fundamentally doing mathematically is A plus negative B. Subtraction is just addition wearing a disguise.
Okay, I want to test that logic on a super basic equation from the text to see how this works for a beginner. Let's say I have the equation x plus 3 equals 5.
Okay, classic algebra problem.
Now, my middle school math teacher taught me a mechanical shortcut. You know, just move the 3 over to the other side of the equals sign and flip it to a minus 3.
Right, the old move and flip.
Yeah, so
Right.
x equals 5 minus 3, which means x equals 2. Done in 2 seconds. But you're saying that shortcut is skipping the actual underlying physics of the math.
It entirely skips the physics.
So how do we solve x plus 3 equals 5 using only properties 1 through 4?
This is a phenomenal exercise in building rigorous mathematical logic. See, we can't just pick up numbers and magically move them across an equal sign.
Because the equal sign is a scale in perfect balance.
Exactly. We have to apply operations equally to both sides to maintain that truth. So we start with our balance scale, x plus 3 on the left, 5 on the right. Step 1, we add the additive inverse of 3 to both sides.
So we add negative 3. Okay, so the left side of the scale now physically looks like x plus 3 plus negative 3. And the right side is 5 plus negative 3.
Correct. Step 2, we invoke property 1, associativity. We use it to logically group the 3 and the negative 3 together on the left side. We're literally telling the system, calculate these two first.
Got it. And step 3, we invoke property 3, additive inverses, to declare that 3 plus negative 3 evaluates to precisely 0.
Yes, so that entire left side simplifies down to just x plus 0.
And then for step 4, we bring in property 2, the identity property. That's the one that states any number plus 0 is just itself. So x plus 0 is just x.
Exactly. And on the right side of the scale, 5 plus negative 3 evaluates to 2. So we finally arrive at x equals 2. Every single microstep, every transformation of that equation was legally justified by one of those 4 fundamental properties.
Okay, I get the mechanical logic, but honestly, this feels like total overkill.
I know it does.
Like, if I have 5 physical apples sitting on a table, and I physically pick up and eat 3 of them, I can look at the table and see I have 2 apples left. I don't need a 4-step logical proof involving additive identities and inverse properties to eat an apple. Why overcomplicate it?
It's a totally valid skepticism. And you're right. Relying on intuition and physical observation works perfectly for apples. It works for tangible objects you can hold in your hands.
Right.
But mathematics doesn't stop at apples. Eventually, you are going to be dealing with abstract concepts. Complex variables, imaginary numbers, multidimensional matrices.
Things you can't just look at on a table.
Exactly. Completely unfamiliar algebraic structures that you cannot visualize or hold. If your foundational habit is just move the number over because it makes sense intuitively, you'll inevitably make a catastrophic error when the structures stop acting like physical apples.
So we are building a framework that protects us from our own limited human intuition.
Exactly. These step-by-step foundational rules are the only way to guarantee mathematical truth when your intuition completely fails you. Let me give you a perfect example of how these rules prove something your intuition takes for granted.
Okay.
Using only properties 1 through 4, Spivak actually proves that 0 is entirely unique.
Unique in what way? Like, it's the only 0.
Unique in that it is the only number in the universe that can act as an identity. Like, what if I told you I found a secret second number, let's call it x, that also acts like 0?
So an equation that says a plus x equals a.
Yes. How do you prove me wrong? How do you mathematically prove that x must be 0 and cannot be anything else?
Well, I assume we do the exact same dance we just did with the apples.
We do. We start with a plus x equal a. First step, we add the inverse of a, which is negative a, to both sides.
Okay, the left side becomes negative a plus x, and the right side becomes negative a plus a.
Right. And on the left side, negative a plus a collapses into 0, leaving 0 plus x. On the right side, negative a plus a also collapses into 0.
Oh, I see. And by property 2, 0 plus x is just x. So the left side is x and the right side is 0. So x equals 0.
We have proven, without a shadow of a doubt, that no other identity can exist. If any number tries to act like 0, the properties physically force it to actually be 0.
It's airtight. It feels less like math and more like highly structured philosophy,
It really is.
So we've built this self-contained sandbox for addition. We can shuffle values left and right on a number line with total security, but addition is slow.
Very slow.
If I want to calculate the total cost of buying 1,000 items, adding them one by one using pairs is wildly inefficient. We need a way to scale reality. We need multiplication.
Which brings us to the next structural pillar of the universe, properties 5 through 8, which govern multiplication. And you'll immediately notice that multiplication mirrors addition beautifully. It's almost a perfect reflection.
Oh, really?
Yeah. Property 5 is associativity for multiplication. It says that A times the grouped pair of B times C is exactly the same as the grouped pair of A times B multiplied by C. You can group your factors however you want.
And I assume property 8 is commutativity then. A times B equals B times A, like 5 times 4 is identical to 4 times 5. The order doesn't matter.
Exactly right.
Yeah.
And just like addition had 0 acting as its identity, the number that changes nothing, multiplication needs its own identity.
Right.
That is property 6. A times 1 equals A. Any number multiplied by 1 remains entirely unchanged. But Spivak adds a very specific, incredibly important caveat to property 6. He explicitly states that 1 does not equal 0.
Wait, what? That sounds almost like a joke. Like, by the way, dear reader, 1 is not 0. Why would a brilliant mathematician waste ink formally declaring that 1 does not equal 0?
Because remember the game we're playing. We are building the universe from absolute scratch. We cannot bring outside knowledge into the sandbox.
Okay, fair.
If we don't explicitly declare that 1 and 0 are different entities, we run into a catastrophic logical collapse. Just imagine a universe where 1 did equal 0.
Okay, let's play that out. If 1 equals 0, then multiplying any number by 1 would be exactly the same thing as multiplying that number by 0.
Yes. And, as we all intuitively know, multiplying anything by 0 destroys it. It turns it into 0.
Yep.
So if 1 equals 0, then a times 1 is 0. But property 6 says a times 1 must equal a. Therefore, a must equal 0.
Oh, wow.
If 1 equals 0, then every single number in existence, no matter what it is forced to equal 0. Everything collapses into a single point of nothingness.
Or the mathematical black hole.
Exactly. The math would still technically obey all the rules, but there would only be one number in the entire universe. So to ensure we have a rich universe with diverse numbers, we have to formally declare that our multiplicative identity is distinct from our additive identity. 1 is strictly not equal to 0.
That is fascinating. We literally have to artificially hold the universe apart to stop it from collapsing.
Yeah.
So we have our identity. Which brings us to property 7, the multiplicative inverse. And this is where things get truly dangerous.
Oh, very dangerous.
Property 7 states that for every number a, there is an inverse, let's call it a inverse, such that a multiplied by a inverse equals 1. And just like you told me subtraction was a lie, I'm guessing division is a lie too.
You are catching on to the grand illusion. Division, as a fundamental standalone operation, does not exist. Just as subtraction is secretly disguised addition, division is secretly disguised multiplication.
Okay.
When you write a divided by b, you are not performing a new kind of math. You are actually writing a multiplied by the inverse of b.
So if I want to divide 10 by 2, I'm actually taking 10 and multiplying it by the inverse of 2, which is 1/2. 10 times 1/2 is 5.
Exactly. This drastically simplifies the foundational order of operations. You do not have 4 fundamental actions to worry about. You only have 2, add and multiply. The other 2 are just applications of inverses.
That does make it cleaner. But I am looking at property 7, and there is a massive glaring warning label slapped on it. It says for every number a except 0, there is an inverse.
Yes, except 0.
And this brings us to a concept that completely baffles beginners and frustrates, elementary school students around the world. Why is dividing by 0 undefined? Like, why is it the ultimate mathematical sin? What actually happens if you try?
This raises an important question, and it's one of the most beautiful pieces of logical deduction in the entire book. Let's really break down Spivak's reasoning here. We just established that division fundamentally relies on finding a multiplicative inverse, right?
Right. To divide by a number, you must be able to multiply by its inverse.
And an inverse is defined as the specific number you need to multiply by to get back to 1.
Like the inverse of 3 is 1/3 because 3 times 1/3 equals 1. Makes sense.
So let's examine 0. What is the multiplicative inverse of 0? By our strict definition, it would be some mystery number that, when multiplied by 0, results in the number 1.
Okay, I'm searching my brain for a number that I can multiply by 0 to get 1.
Keep searching. But keep in mind, another universal rule. Any number, real, imaginary, massive, or microscopic, when multiplied by 0 equals 0. 0 times 5 is 0. 0 times a billion is 0.
So the equation 0 times x equals 1 is impossible.
It is structurally impossible. There is no number in existence that you can multiply by 0 to get 1. The very concept of 0's inverse is logically meaningless. It cannot exist.
Wow.
And because that inverse cannot exist, the entire concept of dividing by 0 collapses instantly. You can't even argue that dividing by 0 equals infinity, because it doesn't.
Right, it's not a really big number. It's an undefined void.
It is asking a question that violates the basic grammar of the universe we just built. It's like asking, what does the color blue taste like? The parameters of the question are fundamentally incompatible with reality.
That is deeply satisfying to finally understand on a mechanical level. Because it's not just an arbitrary rule a teacher made up to be annoying, like, I before E except after C.
Exactly, no.
Yeah. It is a structural impossibility. The machinery simply does not possess a gear that can process that input.
Exactly. And understanding the consequences of property 7, knowing exactly why division by 0 is illegal, but division by literally anything else is perfectly fine, gives us the ultimate power to solve algebraic equations.
How so?
Well, for example, let's say you have an equation, a times b equals a times c. Can you logically conclude that b equals c?
Well, my intuition screams yes. Like, if I have 5 times x equals 5 times y, then obviously x must equal y. I just cancel out the 5s.
Your intuition is right, only if you guarantee that a is not 0. Because if a is 0, then you have 0 times 5 equals 0 times 10. Both sides evaluate to 0, so the equation is mathematically true, but 5 certainly does not equal 10. Your intuition would lead you to a completely false conclusion.
Oh, wow. I see. That's a huge trap.
However, if you know for a fact that a is not 0, then property 7 activates. You are legally allowed to multiply both sides by the inverse of A. The A and the A inverse on both sides combine to form 1. And you are left with 1 times B equals 1 times C, or simply B equals C.
Okay, this is exactly why we can solve those classic algebra problems from high school, right? The ones where you have two brackets multiplied together, like the group x minus 1 multiplied by the group x minus 2 equals 0.
Yes, that is the perfect application. If you have two unknown quantities multiplied together and the result is 0, property 7 guarantees a profound truth. Either the first quantity is 0 or the second quantity is 0.
Right, because it's structurally impossible for them both to be non-zero numbers and still multiply to 0.
Exactly.
So in the equation x minus 1 times x minus 2 equals 0, we can confidently split it into two separate guaranteed truths. Either x minus 1 is 0, which means x is 1, or x minus 2 is 0, which means x is 2. The logic is flawless.
Flawless and incredibly powerful. It is the real workhorse of algebra.
Okay, so far we've built two distinct sandboxes. We have a sandbox for addition with its 4 rules, and we have a separate sandbox for multiplication with its 4 rules.
Yes.
They have similar structures, they both have identities and inverses, but they haven't actually interacted with each other yet. They're totally isolated. But Spivak introduces a 9th rule, property 9, the distributive property.
Yes.
And this is the magic bridge, right? This is the rule that forces addition and multiplication to play together in the same arena.
Property 9 is arguably the most vital operational rule in all of mathematics. It states that A multiplied by the grouped addition of B plus C is exactly equal to A times B plus A times C. The multiplication literally distributes itself evenly over the addition.
Okay.
This single property is a justification for almost all algebraic manipulations, especially factoring.
How does factoring relate to distribution?
Well, when you take a complex quadratic equation, like x squared minus 3x plus 2, and you factor it out into two clean parentheses like x minus 1 times x minus 2, you aren't doing some mysterious dark magic. You are just running property 9 in reverse. You are undistributing the terms to find their root components.
Okay, let's translate this out of abstract algebra and into an everyday, highly practical situation for the listener, because this is so crucial for beginners. Let's look at how the distributive property is the secret engine behind everyday mental math.
I love this example.
Let's say you run a small business, right? You need to buy 13 pieces of equipment, and they cost $24 each. You're standing there at the register, and you need to do 13 times 24 in your head.
Which is not easy.
No, most people do not have their 24 times tables memorized, so what does your brain naturally do?
Your brain instinctively searches for easier numbers to work with. It essentially uses property 9.
Exactly. Without even realizing it, you intuitively split that awkward $24 into a clean $20 bill and 4 $1 bills. So instead of trying to compute 13 times 24 all at once, you reformat the problem. You calculate 13 times the grouped addition of 20 plus 4.
And right there, property 9 takes over. It gives you the legal permission to distribute the 13.
Right. You multiply 13 by 20. That is easy mental math. It's 260. Then you multiply the 13 by the 4. Also relatively easy. It's 52. Finally, you just add those two separate products together. 260 plus 52 gives you a final total of $312.
It's a brilliant example. It shows exactly how distribution dictates the order of operations and makes complex math manageable. I mean, even when you were back in 4th grade doing multi-digit multiplication on a piece of paper, where you multiply the ones column, carry the number, multiply the tens column, shift the next row over with a 0.
Yeah, the classic method.
That entire mechanical process is just a visual algorithm for executing property 9.
But the utility of property 9 goes way beyond just calculating grocery bills. Here's where it gets really interesting. Spivak doesn't just use property 9 to do arithmetic. He uses it to prove two fundamental truths about the universe that literally everyone takes for granted, but almost no one can actually prove if you ask them.
Oh, these are great. Let's tackle the first one.
Yeah. Earlier, you stated that any number multiplied by 0 equals 0. We all know this. A billion times 0 is 0. But why? How does property 9 logically prove that a times 0 is 0?
This proof is an absolute masterpiece of elegance. We start with a clever, completely legal trick. Let's just write down the expression a times 0 plus a times 0.
Okay.
Now, looking at that, we can use the distributive property in reverse. Both terms have an a being multiplied, so we can factor that a out.
Okay, so if we pull the a out, the expression becomes multiplied by the group of 0 plus 0.
Precisely. Now let's look inside that parenthesis. What is 0 plus 0? Property 2, 0 is the additive identity. Anything plus 0 is itself. So 0 plus 0 is simply 0.
Right. That's undeniably true.
So the right side of our equation simplifies from a times the group of 0 plus 0 down to just a times 0. Now let's look at the entire equation we've built. We started with a times 0 plus a times 0, and we just proved that it equals a times 0.
Wait, it looks like an equation saying x plus x equals x?
Exactly. Let's treat a times 0 as a single block, a single variable. Let's call it block y. So we have y plus y equals y. How do we solve this? We do the exact same thing we did when proving 0 is unique. We add the negative inverse of y to both sides.
So we add the inverse of a times 0 to both sides. On the left side, we have two of these blocks. One of them gets canceled out by the inverse, leaving just one a times 0 block.
And on the right side, we had one a times 0 block. We add the inverse to it, and any number plus its inverse is 0.
So the right side becomes 0, and we're left with the final undeniable conclusion. A times 0 equals 0.
It is airtight logic. We literally weaponized the fact that 0 plus 0 equals 0 and distributed an a across it to definitively prove that multiplication by 0 destroys any number.
That is beautiful, but the second proof is the one that really gets people. It is the holy grail of confusing elementary math.
Oh, yes.
Why does a negative times a negative equal a positive? If I stop an adult on the street and ask them why -2 times -3 is +6, they will probably laugh and say, I don't know, 2 wrongs make a right. The minuses cancel out.
Right. It's just a rote rule we memorized to pass a test.
Yeah. But Spivak says it is a forced, unavoidable consequence of the universe we have built. So let's map it out.
Let's do it carefully, step by step. Our goal is to understand the true identity of the expression -a times -b. What is it really? To find out, we start by looking at a different related equation. Let's look at the expression. -a times +b plus +a times +b.
Okay, looking at that, I see a common factor. Both parts are being multiplied by b. So by property 9, the distributive property, I can pull that b out.
Yes. Factor out the b. The expression transforms into the grouped addition of -a plus a, all multiplied by b.
I see where this is going. Inside that group, we have -a plus a. Those are additive inverses. By property 3, they annihilate each other. -a plus a is exactly 0.
Right, so the parenthesis becomes 0. We now have 0 times b. And we literally just proved moments ago that anything times 0 is 0.
Yes, we did.
So that entire original expression, -a times b plus a times b, evaluates to exactly 0.
Let me summarize what we just established. We added two things together, and the result was 0.
And what does that mean structurally? If adding two things gives you 0, they must be exact inverses of each other. This proves that -a times b is the exact opposite of +a times b. In simpler terms, a negative times a positive results in a negative.
Yeah.
We have formally established that baseline first.
Okay, that makes intuitive sense. Like if I owe 3 people $5 each, I have -$15. Negative times positive is negative. But now for the grand finale, how do we get to negative times negative?
Now we set up the final equation to trap our suspect. Let's look at this expression. -a times -b plus -a times +b.
Okay, analyzing this, I see another common factor. Both terms have a -a in them.
So we distribute again, we factor out the -a, the expression becomes -a multiplied by the grouped addition of -b plus b.
The trap springs. Inside the group, -b plus b are inverses. They annihilate each other and become 0.
Yes. So we are left with -a times 0, which, by our ironclad rule, is 0. So our whole massive equation simplifies to this profound statement. -a times -b plus -a times +b equals 0.
Okay, let me translate this into pure logic so I can wrap my head around it. We have this mysterious unknown entity called -a times -b. We take it and we add it to -a times +b, which we just proved is a negative number. When we add them together, the scale perfectly balances at 0.
Therefore, to perfectly balance a negative number to 0, that mysterious first entity must be its exact positive opposite. Since the second term is -a times b, the first term must be +a times b.
Right.
Therefore, we conclude with absolute certainty that -a times -b equals +a times b.
That is genuinely incredible. It's not an arbitrary rule decided by a committee of grumpy mathematicians in the 18th century. It is a forced, structural consequence.
Exactly.
If you want properties 1 through 9 to be true in your universe, like you want to be able to add, multiply, and distribute values, you have to accept that a negative times negative is positive. You cannot have the convenience of distribution without accepting the reality of negatives canceling out.
It is a load-bearing pillar of the universe. If you try to change that single rule, say you decide a negative times the negative should stay negative, you instantly break the distributive property, which breaks multiplication, which just shatters the entire framework.
Wow. So what does this all mean for us? We have established these 9 properties. They give us the absolute mechanics to calculate. We can shuffle numbers around. We can balance scales. We can calculate that 13 items at $24 is $312. We basically have a functioning calculator.
We do.
But there is a massive blind spot. These 9 properties do not tell us how numbers relate to each other in terms of size.
That is the blind spot. Properties 1 through 9 define what mathematicians call a field. But in the real world, to do practical things like measure the physical distance between 2 cities or determine if you actually have enough money in your bank account to buy that coffee, you need a way to order the numbers.
You need to know who is bigger and who is smaller.
Exactly. You need inequalities.
And Spivak introduces this ordering system with properties 10, 11, and 12 by establishing a concept of a collection of positive numbers, which he denotes with the letter P.
Think of this collection P as the directional compass for reality. Without set P, numbers have no gravity. They just float in an undefined, directionless space. Set P establishes the concept of up. And by establishing up, it forces the rest of the numbers to orient themselves as down.
I love that metaphor. The positive numbers are up. How does this compass actually work?
It starts with property 10, known as the trichotomy law.
Trichotomy law.
The name sounds intimidating, but the concept is deeply intuitive. It states that for every single number A in existence, exactly one of 3 mutually exclusive things is true. Option 1, A is 0. Option 2, A lives in the positive club P. Option 3, negative A lives in the positive club P.
Okay, let me relate the trichotomy law to comparing real-world values so we can ground this for beginners. Say I'm looking at my bank balance and I'm comparing it to the cost of a new laptop.
Great example.
Let's call my balance A and the laptop cost B. When I mathematically compare them by subtracting B from A, the result can only fall into one of 3 buckets. Bucket 1, my balance is greater than the cost, so A minus B is a positive number. Bucket 2, the cost is greater than my balance, so A minus B is a negative number. Bucket 3, they are exactly equal down to the penny, so A minus B is 0.
That's about on.
There's no mystical fourth state where they're both greater than each other, or neither is greater nor equal. It's absolutely definitive.
That is a perfect practical application, and Spivak uses this exact logic to define what greater than actually means. We use the symbol for greater than all the time, but what does it mean?
Right.
When a mathematician writes A is greater than B, all they are functionally saying is that the calculation of A minus B results in a number that belongs to the positive club P.
So if my balance is $1,000 and the laptop is $800, 1,000 is greater than 800 purely because 1,000 minus 800 evaluates to 200, and 200 is a resident of the positive club P. It all ties back to the compass.
But for the compass to be reliable, the positive club P needs strict entry rules. That is where properties 11 and 12 come in. They're called the closure laws.
Closure laws, okay.
Property 11 dictates that if A and B are both in the positive club, then their sum, A plus B, is also permanently trapped in the club. Adding 2 positive numbers always yields a positive number. Property 12 states that if A and B are in the club, their product, A times B, is also in the club. Multiplying positive numbers always yields positive numbers.
Again, on the surface, this feels like we are defining the most obvious things in the world. 2 positive things make a positive thing. But I'm sensing another trap. I know these simple rules are going to lead to a profound, inescapable conclusion.
They absolutely do. These 3 simple rules, the exclusivity of trichotomy and the 2 boundaries of closure, lead to a massive mathematical consequence.
Which is?
The square of any non-zero number is always positive.
Okay, let's trace that logically. Why is a square forced to be positive?
Let's pick a random number A that is not 0. According to the trichotomy law, there are only 2 possibilities for A. Either A is positive or negative A is positive. Let's explore case 1. A is positive. By property 12, the closure of multiplication, if we multiply A by itself, the result must stay in the positive club.
So A times A, which is A squared, is definitively positive.
Right.
Okay, that was the easy path. What if A is a negative number, say negative 5?
If A is a negative number, trichotomy dictates that its inverse, negative A, must be the one in the positive club. So negative a is our positive value. Let's multiply that positive value by itself. Negative a times negative a. By the closure law, positive times a positive must be positive.
Wait, and earlier we did the hard work of proving that a negative times a negative is a positive. We proved that negative a times negative a is exactly equivalent to a squared.
Yes, therefore, a squared is positive.
In both possible paths, the universe forces the square to be positive.
Yes. And this universal truth leads to something that looks so elementary, it is almost insulting to write down. Using this, we can finally prove mathematically that 1 is greater than 0.
It seems ridiculous that we have to prove that.
It seems ridiculous, but think about the journey we've been on. Until this exact moment in Spivak's framework, we had 0 mathematical proof that 1 was a positive number. We knew 1 existed because it was the multiplicative identity, but identity doesn't imply positivity. But now, look at the number 1. 1 is equal to 1 squared because 1 times 1 is 1.
Oh, wow.
And we literally just proved that the square of any non-zero number is forced to be positive.
Therefore, because 1 is a square, 1 must be positive, which means 1 is greater than 0.
Exactly. We had to invent the concept of multiplication, the concept of inverses, prove that a negative times a negative is a positive, establish a positive compass, define trichotomy, and enforce closure laws, all just to definitively prove that 1 is a positive number.
That is wild. But if you think about it, proving 1 is greater than 0 is fundamentally necessary for the rest of reality to exist. If you cannot mathematically prove that 1 is up on the compass, you cannot prove that 2 is up, or that you can count upwards at all, the number line would have no direction.
Exactly. It anchors reality.
I do have a point of confusion I want to bring up, especially for people trying to read this text or learn logical notation. Spivak points out a very weird quirk about the less than or equal to sign. You know, the symbol that is an arrow with a little horizontal line under it.
Yes.
He notes that the mathematical statement 1 plus 1 is less than or equal to 3 is evaluated as true. But the statement 1 plus 1 is less than or equal to 2 is also evaluated as mathematically true. How does the logic reconcile that? We know for a fact that 1 plus 1 is strictly precisely equal to 2. It feels like we are lying to the system when we say it's less than or equal to.
That is a very common source of friction. It comes down to how formal logic systems process the English word. Or, in casual conversation, if I say, I'm going to the movies, or I am staying home, I mean, one or the other, but not both.
Right.
But in strict mathematics, when a statement says A is less than or equal to B, the entire statement is considered true if at least one of those conditions is satisfied.
So because 1 plus 1 equals 2, the equal to half of the condition is satisfied.
Exactly. The logic gate checks the less than side, sees it as false, then checks the equal to side, sees it as true. Since one side is true, the whole gate opens. It evaluates as true. It does not mean the mathematician is unsure of the exact value. It is simply a broader logical net that catches more truths.
I see.
It becomes incredibly useful in higher math when you are dealing with unknown variables where you don't know the exact pinpoint value yet, but you absolutely know its upper ceiling.
Okay, that makes sense. It's like me stating, I'm either sitting in this chair or I'm currently walking on the moon. It's technically a mathematically true statement because I am in the chair, even though the moon part is wildly false. The logic gate opens.
That is a perfect way to visualize it.
All right, so we now know how to order numbers. We know who is bigger, who is smaller, and who is the ceiling. But in reality, sometimes direction doesn't matter. Sometimes you just care about the raw gap between things. Which brings us to the concept of absolute value, distance, and how we measure the world.
Absolute value is denoted by those two straight vertical bars around a number. And it is formally defined by splitting reality into cases. If A is positive or 0, the absolute value leaves it alone. It is just A. But if A is negative, the definition states the absolute value is negative A.
Wait, I remember learning that absolute value just meant erase the minus sign and make it positive. Why does the formal definition explicitly say negative A? That sounds like it's making it negative.
Think carefully about what negative A actually means in algebraic terms. If A is already a negative number, like negative 5, then the instruction negative A means negative negative 5. What did we prove earlier about two negatives?
They made a positive, so negative 5 becomes positive 5.
Precisely. So saying the absolute value of a negative number is negative A is mathematically forcing it to become positive. It is an algorithmic machine that purposefully strips away the direction. The absolute value of any number is always positive, except for 0.
Got it. And Spivak uses this machine to introduce Theorem 1, which is famous in mathematics, the triangle inequality. The formula is written as the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of b. This looks like alphabet soup to a beginner. What is this equation actually describing about reality?
Let's break it down by looking at the different possible cases, which is the rigorous step-by-step approach Spivak initially takes. Let's look at case 1. Both a and b are positive numbers. Let's use 2 and 3. On the left side of the formula, inside the bars, 2 plus 3 is 5. The absolute value of 5 is 5.
Simple enough.
On the right side of the formula, we separate them. The absolute value of 2 is 2. The absolute value of 3 is 3. 2 plus 3 is 5. So the formula says 5 is less than or equal to 5. Since 5 equals 5, the logic gate opens. It is true.
Easy. And I assume case 4, where both are negative, works the same way. Like if a is -2 and b is -3, inside the bars they combine to -5. The absolute value machine strips the sign, making it 5.
Right.
And separately on the right side, the absolute value of -2 is 2. The absolute value of -3 is 3. 2 plus 3 is 5. So again, 5 equals 5.
Exactly. If the signs are identical, if they are pushing in the same direction, they work together, and the formula is a straight equality.
Mm-hmm.
But the magic, the real insight, happens in case 2, where they have mixed signs. Let's say a is +5 and b is -3. Let's run the formula.
Okay, left side first, inside the single set of bars. 5 plus -3. That evaluates to 2. The absolute value of 2 is simply 2. That is our left side.
Now the right side. We process them through the absolute value machines first, before adding. The absolute value of 5 is 5. The absolute value of -3 is forced to be +3. Now we add them. 5 plus 3 is 8. So the final equation reads, 2 is less than or equal to 8.
Ooh. I see the mechanics of it now.
Yeah.
Because one was positive and one was negative, they fought against each other inside the single parenthesis on the left, pulling the total combined value down to 2.
Exactly.
But on the right side, when you take their absolute values first and isolate them, you strip away their opposing directions, you force them to work together in the same positive direction. So the separated version on the right will always be bigger, or at least equal.
You nailed it. That is the essence of the triangle inequality. And while grinding through all those positive and negative cases works, Spivak also outlines a much faster, more elegant algebraic proof using squares. Instead of testing numbers, you just mathematically square both sides of the inequality.
How does squaring it help?
We know from basic algebra that the quantity x plus y squared expands into x squared plus 2xy plus y squared. Yeah. So the left side of our formula, the square of the absolute value of a plus b, expands into a squared plus 2ab plus b squared.
Okay, I'm visualizing that.
And the right side, the square of the quantity absolute value of a plus absolute value of b, expands similarly into a squared plus 2 times the absolute value of a times the absolute value of b plus b squared.
I see the trap. The a squared and b squared terms are identical on both sides of the equation. They balance each other out perfectly. The only difference between the left and right side is that middle term, 2ab on the left versus 2 times the absolute values of a and b on the right.
Exactly. And we know intuitively that a raw number, ab, which could potentially be negative, can never physically be larger than its forced positive absolute value. So the right side must be mathematically greater than or equal to the left side. It is a gorgeous one-line proof that entirely bypasses all the messy, time-consuming case-by-case logic.
That is deeply satisfying, but I want to extrapolate this out of the textbook. How does this apply to real-world problems? Because in the problem set at the end of the chapter, specifically problem 13, Spivak introduces these fascinating, slightly terrifying formulas.
Yes, the max and min formulas.
Yeah, he provides a universal formula to find the maximum of any two numbers, x and y. It is x plus y plus the absolute value of y minus x all divided by 2, and a corresponding minimum formula, x plus y minus the absolute value of y minus this all divided by 2. Now, as a human being, if you show me the numbers 5 and 3, I don't need a massive fraction with absolute values to tell you 5 is the maximum. Why on earth would someone invent this complicated formula?
Because computers do not have eyes, and they do not have human intuition. As a human, you can eyeball 5 and 3. But imagine you're a software engineer writing a program for a high-frequency trading algorithm. Your program has to compare 1 billion pairs of fluctuating stock prices every single second, and it needs to instantly isolate the highest value to make a trade. If you write code using complex if-then logic, like if x is greater than y, then output x or else output y, that branching logic takes processing time, slows the computer down. This absolute value formula operates as a flat, universal algorithm that calculates the answer mechanically without needing to think or branch.
Let me test the mechanics of that algorithm to see if it really works. Let's say variable x is 3 and variable y is 7. I feed them into the max formula. First part, x plus y is 10. Second part, The absolute value of y minus x, so 7 minus 3 is 4. The absolute value of 4 is 4.
Right.
So the top of the fraction is 10 plus 4, which is 14. Divide by 2, you get 7. The formula successfully spit out the maximum number.
Now try feeding it into the machine backwards. What if x is the big number? Let x be 7 and y be 3.
Okay, x plus y is still 10. Now for the absolute value part, y minus x is 3 minus 7, which evaluates to negative 4. But the absolute value machine strips the negative, turning it back into a positive 4. So the top of the fraction is once again 10 plus 4, which is 14. Divided by 2 is 7. It works perfectly. It does not matter which order you feed the data in, the absolute value acts as an automatic balancing mechanism that always forces the math to land on the large number.
It translates abstract inequalities into a highly practical, mechanical tool for solving complex logic problems in programming. It is the bridge between pure math and computer science.
So if we step back, what does this absolute value concept mean for the average person living their life? The way I visualize it is simply physical distance. If I stand in the center of town and walk 5 blocks north, or I walk 5 blocks south, my displacement on a coordinate grid is different. One is positive 5, one is negative 5.
Exactly.
But the absolute value, the actual physical distance my legs traveled, the calories I burned, the wear and tear on my shoes, is 5 blocks either way. Absolute value strips away the arbitrary concept of direction and leaves you with the raw magnitude of the distance between 2 points in everyday life.
That is the perfect analogy. And if you map the triangle inequality onto that physical space, it literally proves mathematically that the shortest distance between 2 points is a straight line. Taking a detour, which is represented by separating the absolute values into 2 distinct trips, will always result in a longer, or at best equal, path. The math perfectly describes the physical reality.
We have covered an immense amount of ground. We have built up this massive interlocking structure of 12 rules. We have addition, multiplication, the distributive bridge, ordering, positive compasses, and distance. Everything seems absolutely airtight.
It does.
But I want to push the boundaries. What happens if we selectively ignore some of the rules? This brings us to the philosophical climax of the material. I want to revisit a dangling thread from much earlier in our conversation.
I know exactly the thread you mean. Let's look back at a proof Spivak mentions early on. He states that if the distance from A to B is exactly the same as the distance from B to A, then A and B must be the exact same point. Algebraically, if A minus B equals B minus A, then A must equal B.
Right. It makes perfect logical sense.
But the way he proved it algebraically was incredibly tricky. He rearranged the equation to get all the A's on one side and B's on the other, resulting in A plus A equals B plus B. Then, he factored both sides using the distributive property. He pulled out the variables to get A times the group 1 plus 1 is exactly equal to B times the group 1 plus 1.
And from there, it's basic algebra. You just divide both sides of the equation by the group 1 plus 1, which is 2. The 2's cancel out on both sides, and you're left with A equals B. The proof is complete.
But let's look at the microscopic legal details of what you just did. To divide by 1 plus 1, you have to multiply both sides by its inverse. And property 7, our rule for inverses, has a massive warning label. It says you can only find an inverse if the number is not 0. So to legally execute that final step of the proof, you had to be absolutely 100% mathematically certain that 1 plus 1 does not equal 0.
I mean, come on. 1 plus 1 is 2. 2 is not 0. If I have 1 apple and you give me another apple, I do not suddenly have 0 apples.
It is come on to us because we live in this physical reality and we assume we know what numbers are. But Spivak introduces problem 25 at the end of the chapter, which is a massive reality-bending curveball.
Okay.
Because imagine a completely bizarre alien number system that only contains 2 numbers in its entire existence. 0 and 1. Nothing else exists. And in this system, the rules of addition are defined as 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and incredibly, 1 plus 1 equals 0.
Whoa, so 1 plus 1 hits a ceiling and wraps back around to 0.
Exactly, like a clock hitting midnight and resetting to 0 hours.
Mm.
It is called modular arithmetic. Think of it like a light switch. Off is 0, on is 1. If the switch is on, so that's a 1, and you flick it on again, so you add 1, it goes to off, which is 0.
Okay, I can visualize that alien universe, but how does that affect our 12 rules?
Here is the mind-bending part. In this 0 and 1 clock universe, you can test all of our foundational rules. Associativity works perfectly. Commutativity works perfectly. 0 acts as the perfect identity. Inverses work because 1 is its own inverse since 1 plus 1 is 0. Multiplication works. The distributive property works seamlessly. In this bizarre looping system, properties 1 through 9 still hold entirely true.
Wait, I need to process this. You were telling me that we spent all this time building those first 9 foundational rules of math, rules we thought defined our physical reality, and they're perfectly happy existing in a universe where 1 plus 1 equals 0.
Yes, and this is the ultimate lesson in analytical, rigorous thinking. It is the realization that we could not simply assume 1 plus 1 wasn't 0 using only the rules of addition and multiplication, because those 9 rules are completely blind.
Oh, wow.
They don't care if numbers keep getting bigger infinitely or if they loop back on themselves like a clock. The mechanics of P1 through P9 do not guarantee our version of reality.
So how did we save the math? How did we lock in our reality and prove that 1 plus 1 does not equal 0?
We needed the inequality rules. We needed properties 10 through 12. We needed to invent the compass. We needed the concept of the positive club P. Think back to our earlier proof. We used trichotomy and closure to definitively prove that all squares are positive, which in turn proved that the number 1 is greater than 0.
Yes, I remember. 1 is officially in the positive club.
Well, if 1 is in the positive club and you add another 1, which is also in the positive club, the closure of addition, property 11, dictates that their sum, 1 plus 1, must also be permanently trapped in the positive club.
Okay, yeah.
Therefore, 1 plus 1 must be strictly greater than 0. And if a number is greater than 0, the trichotomy law guarantees that it cannot simultaneously be 0. Therefore, we have rigorously proven that 1 plus 1 does not equal 0.
I am genuinely amazed by the architecture of that, the way the different systems locked together to save the proof. We needed the inequality properties to act as the structural cross-bracing to stop the addition and multiplication properties from collapsing into a loop. It shows that numbers aren't just vague historical symbols we memorize in grade school to count inventory. They are complex entities, entirely defined and constrained by a strict, unbreakable set of interconnected logical rules.
Spivak concludes this section with a profound thought. He suggests that we don't fully understand what numbers actually are in some deep philosophical sense. But whatever these entities are, they must obey these 12 rules, or the whole system fragments. Exploring this is not about memorizing tricks to pass an algebra test. It is not about simply moving a 3 to the other side of an equation.
Right.
It is about building a robust, infallible chain of reasoning where every single microscopic step is justified by a foundational law. It trains the mind to think critically, to identify hidden assumptions, and to construct a truth so deeply rooted that no one can ever dismantle it.
That is a phenomenal takeaway. And it brings us to the end of this incredibly intense foundational journey. We have stripped the concept of numbers down to their 12 atomic properties. We rebuilt everything from the architecture of basic addition and the terrifying void of dividing by 0 all the way to the absolute limits of physical distance and the structural integrity of the number 1.
We really did. It forces a completely different perspective.
Yeah.
You will never look at the change in your pocket or the formulas in a spreadsheet the same way again.
But before we close out this deep dive, I want to leave you with a final, slightly haunting thought to ponder on your own. We have spent this entire time establishing these 12 rules, these absolute pillars that govern our numerical reality. We have proven that they keep the math safe and prevent the universe from looping back on itself.
Yes.
But at the very end of this chapter, Spivak hints at a dark secret. He hints that these 12 properties actually aren't enough to account for all the behaviors of numbers. There is hidden deficiency, a microscopic gap in the armor.
A missing property that requires diving into entirely new, infinitely deep dimensions of mathematics to discover and articulate.
Exactly. If these 12 rules perfectly describe the math we use every day to buy coffee, sell laptops, balance ledgers, and measure the distance between cities, what could possibly be missing? We leave you to wonder about the mathematical ghosts hiding in plain sight, living in the gaps between the numbers you trust with your life every single day.